Hi, we are junior high school students in AP Physics 1.
We're going to be testing the concepts of the conservation of linear momentum and the impulse momentum theorem.
And we are the Gentlebots. So here we have our lab setup. We have two motion detectors connected on either side, both going to the same lab quest and putting our data right there. As you can see, we have two masses right here that are protecting the sensitive parts of the motion detectors from being hit by the car as they move back and forth. If you look over from a bird's eye view right here, you can see our bubble level is proving that our surface is flat, so the angle of the track does not affect our data at all. And then we have two carts here that will be hitting each other. On these sides there's magnets, and when facing each other, they'll have a perfectly elastic collision and bounce off of each other. And then here's our non-elastic collision with pretty much just plastic on plastic. And then if you flip this one over, there's Velcro on both sides of these where they will stick together when hit. And then we also have, we flip one of these carts, there's buttons that can release a plunger. That will be the same force applied every time as long as you push the plunger in at the same interval backwards that will eject this cart.
This is something most people have heard about, but might not know exactly what it is. And so conservation of momentum is that when we have the initial momentum of a system, it will be equal to the end momentum of a system. However, there's a key idea is that it has to be a closed system, and it can have any influence from anything on the outside, because then so it's no longer a closed system. So let's do an example with something that's been quite relevant to our experiment. It's going to be two cars driving at each other. This first car is going to have 1 kilogram, and it's going to be at 10 meters per second. The second car is going to have 2 kilograms and move at, let's say, also 10 meters per second. So first what we're going to do is we're going to check the momentum of each one. And we're going to say, okay, this one has 10 kilogram meters per second. This one has 20 kilogram meters per second. However, you have to notice we decide one of these directions positive, one of these a negative. So I'm going to prefer making positive to the right direction positive. So we're going to make this negative, and we're going to add these together to find the total momentum of the system. So we're going to get negative 10 kilogram meters per second. And then when we have, I'll just do it up here. Afterwards, we can assume that the carts will go the opposite direction that they were initially going. We're going to assume they both kept the same mass. Let's just say the 10 meters per second one goes back at the same speed. Or 10 meters per second. So now it's going to the left, so it's going to be negative 10. So now we have this negative 10 kilogram meters per second. And so we're looking, how fast should the 2 kilogram car be going? And so we're going to plug it in. We have negative 10 kilogram meters per second plus 2 kilograms times some x meters per second. And this will have to equal negative 10 kilogram meters per second. When you do the algebra, you'll have 2 kilograms times x meters per second will equal 0 kilogram meters per second. And so it's actually going to be stationary if this collides off and goes back at the opposite speed.
That's my fault.
3, 2, 1, now. It works.
Alright.
3, 2, 1, go.
Is that clean?
That graphic.
Alright.
3, 2, 1, now.
Damn it.
So here we have a pretty similar setup, except we have a force probe on this side that will measure the amount of force push on this little prong right there. On the opposite side, we have our motion detector, which will detect how fast this cart is moving. They're both plugged into the same lab quest right here, so we get the data at the same time. And for our experiment, we will be pushing this car at different speeds and with different weights into the force probe and measuring the force inputted onto this device.
The last idea is going to be the impulse momentum theorem. What this states is actually quite clear once you think about it for a second. But it starts off with the definition. We'll have impulse is going to be equal to the change in momentum. I just set it right here. So we have this car going along. Let's go 1 kilogram, 10 meters per second. Keep it easy. So we have 10 kilogram meters per second. And then all of a sudden it's going to hit this gust of wind that's going to be applying for, that's going to be 10 newtons for 2.5 seconds. Now, what we can use is this formula right here for impulse. So we have 10 newtons times 2.5 seconds, that's going to be exerting 4. So the momentum is now going to be 25 kilogram meters per second. And so we have negative 25 kilogram meters per second equals the change in momentum. So we have our momentum final, which is this 10. And we're gonna have to find some x that we can plug in here. It's one step problem and it ends up being negative 15 kilogram meters per second, which means after this gust of wind hits, the car is now going the opposite direction with a momentum of 15 kilogram meters per second. And because it's 1 kilogram, we can also state that it's going to be going that direction at 15 meters per second.
That was bad. This is so trash.
First off, the totally elastic collision. This is pretty simple. We threw the two cars at each other and they got repulsed by the magnet. So what we did, we found the initial mass of both cars. We found the initial velocities and the final velocities of the two cars. And since we know momentum is mass times velocity, we were able to get the initial momentum of each car and the final momentum. We could add the initial momentum to the two cars to get the initial momentum of the system and the final momentum of the system. We know since we're testing the conservation of momentum here, we're expecting the difference between these two as be as small as possible. We did the same method for the totally inelastic and inelastic collisions. We slowly made our way to find the momentum of the system, find the difference. Our totally inelastic collision, our first glaring error point is right here. It's going to be right here on our graph. You can see it's well away from the line. This data point, you can see there is a high amount of mass involved in the system. It's about 1,250 grams. It's less than this, but it's still a lot of mass, so it could have thrown something off. Then inelastic, we also have this error point. Again, we had a lot of mass, could have thrown something off. The explosion looks a lot different. There's a lot of zeros. This is because we started with an initial velocity for 0 for both of them before we launched them apart. So the initial momentum of the system is always going to be 0, and the final momentum, we want to be as close to 0 as possible. We want the two cars going away from each other with the same momentum. See, for the most part, we're relatively close. Bottom one's pretty thrown off, but again, really high mass. So it's very likely that the high mass was the issue, possibly causing cars to get bumped off of the track, maybe causing issues with the friction. There's a whole host of problems, but those are probably the two most likely that caused it. And then we can look here. We can see that there's approximately that the approximate linear relationship, when we assume that there's a intercept at 0, is going to be about 0.92. And what we're looking for, since the initial momentum and the final momentum should be the same, initial momentum on the x and final on the y, we're expecting it to just be a straight diagonal line with y equals x to be our slope. And so we're pretty close, but then it's going to be 7.84% error. Although what is interesting is that if we remove a few of our really bad data spots, like the few that we think was caused by the high mass, and we move, I'll just move the title out of the way. Okay, we have only about 1% error to 1.15. So very small error once we get rid of those 3 rogue points in our data.
So a similar source of error is when we have two cars with highly unbalanced weights. When we launch them together, they got off the tracks pretty easily, which causes increased friction.
And then over here, this is going to be our impulse momentum testing. What we did first was find the impulse. There's a really nice function on the tools that we're using. It allowed us to find the amount of force that was average force over a certain amount of time that was exerted, and that would be equal to the impulse. Remember, that's the definition of impulse, is average force times the time that it occurs over. And then we were also able to find the initial final velocity of the car as well as its mass. This allows us to find its initial momentum and final momentum. So we have a change in momentum, and impulse is by definition change in momentum, so we want these to be as equal as possible again. So we're looking for a slope of 1 on the graph. You can see pretty far off. We have the 0.68, that's 31.9%, that's pretty far off.
So one of our sources of error, we believe, is when we put actually too much weight on one of these carts and launch it into the force probe. We'll do it a little faster to get a better demonstration. As you can see, it comes off the tracks here and it causes increased friction coming backwards.